Welcome everyone. My name is Ricardo, and this is a presentation of my poster titled PEGMEA-Porphyrin fluorescent hydrogels and its heavy metal ion detection. Hydrogels have been considered as a promising materials in myriad applications such as drug delivery system, adhesives, wound healing, tissue engineering, agriculture, environmental remediation, among others. The term hydrogel refers to cross-linked polymeric matrices capable of absorbing large quantities of water without dissolving. These networks, composed by hydrophilic chains, are disposed in a three-dimensional arrangement. Hydrogels present soft and elastic structures, being the swelling ability their most important feature, which provide them a wide range of potential applications. There are different ways to prepare hydrogels. We have chosen to use frontal polymerization, which is a process that occurs when an external stimulus is applied in a localized area of a monomer initiator mixture. This reaction generates a self-sustained polymerization front, which propagates in a directional way throughout the reaction vessel. Frontal polymerization has some advantages over traditional polymer synthetic techniques, which makes this method ecologically friendly and energetically effective. High efficiency of conversion of monomer into polymer. Generally, the conversion is more than 99%. Second, simple and easy protocols. Third, short reaction times. Frontal polymerization generally require only a few minutes to convert the mixture of monomers, while classical polymerization techniques often need long reaction times. Fourth, low energy consumption. The external stimulus is only applied until the propagation was formed. Fifth, frontal polymerization is a solvent-free polymerization process. The composition of the synthesized hydrogel is polyethylene glycol, which is a polyether with high water solubility, high hydrophilic character, and good biocompatibility. In addition, a monomer derived from tetraphenylporphyrin that are macrocycles, which is characterized by a well-known absorption and emission spectrum. In this work, we present the results toward the synthesis of a new series of polymer hydrogels obtained by frontal polymerization using a porphyrin derivative monomer as fluorescent moiety in a polyethylene glycol methyl ether acrylate matrix. The optical properties of the obtained hydrogel were studied by fluorescence spectroscopy in solid state, where we can observe an emission band at 655 nanometers in addition to an evident purple coloration due to the presence of porphyrin, more to show a clear emission when is irradiated with UV light. 10 metal ions were chosen to study the metal ion selectivity of the PEG-TPP hydrogel. Figure 2 illustrates the fluorescence intensity of the PEG-TPP hydrogel after immersion in different metal ion aqueous solution containing copper 2+, copper plus, iron 3+, zinc 2+, lead 2+, cobalt 2+, calcium 2+, nickel 2+, cadmium 2+, and manganese 2+, and a solution without metal ions, a blank, at 420 nanometers excitation. We can observe a decrease in the emission intensity of the hydrogel after immersion in the metal ion aqueous solution, but it is worth noting the response of copper 2+ and cadmium 2+ ions, which almost completely quenching the emission. For further study of the sensitivity of the metal ion detection of the PEG-TPP hydrogel, copper 2+ and cadmium 2+ were taken as an example, since these metal ions shows the highest emission quenching. The fluorescence emission spectra of the PEG-TPP hydrogel in the presence of different concentration of copper 2+ and cadmium 2+ ions are shown in figure 3. The reason for PEG-TPP sensitivity to metal ions copper 2 plus and cadmium 2 plus is ascribed to the functional groups porphyrin included in the structure, and on the other hand, it's the high swelling of PEG-TPP that makes metal ions penetrate inside of the hydrogel swiftly. The addition of a little copper 2 plus and cadmium 2 plus leads to significant quenching of the fluorescence emission from PEG-TPP hydrogels. For the 0.25 molar ion solutions, at 99.5% decline in intensity at 655 nanometers is observed, demonstrating the high detection capacity of the hydrogel. The absorption kinetics of the PEG-TPP hydrogel was investigated from 50 micromolar to 0.25 molar copper 2 plus and cadmium 2 plus aqueous solution, as figure 4 shows. The PEG-TPP hydrogel immersed in a copper 2 plus aqueous solution reached the absorption equilibrium after 5 days. Meanwhile, PEG-TPP hydrogel immersed in a cadmium 2 plus aqueous solution reached the absorption equilibrium after 7 days. However, the response to the naked eye can be seen after a few hours of starting the experiment. In conclusion, the synthesis of a new series of PEG-based polymers containing porphyrin moieties PEG-TPP was successfully achieved by frontal polymerization. The obtained hydrogel showed a good response to heavy metal ion detections, particularly copper 2 plus and cadmium 2 plus exhibit significant and visual sensitivity to low concentration of these specific heavy metal ions. Thank you for watching my poster.